Hello, everyone, and welcome to today's webinar, Improved Arc Flash Safety, a 5-point approach to data center design and operations, brought to you by Starline, a brand of Legrand. I'm your host, Gary Cohen. Very happy to be with you today on behalf of Consulting Specifying Engineer. Before we get too far, just a few tools and troubleshooting steps that you may need during today's session. We'll talk first about the webcast console. Please type any questions you have for our speakers in the Q&A widget that's located right below the slide presentation. Our live Q&A session will start in about 45 minutes. Today's webcast is being recorded, and you'll receive an email with a link to the on-demand event. To download a PDF copy of the presentation and a certificate of completion, use the Additional Resources widget on the right side of the webcast console. Those documents will also be available with the on-demand version of this webcast. If you're like me, you need to see things a little bit bigger. You can also expand your view of the slides by using the icon in the top right corner of the slide widget. Here are a few tips and tricks. If you're experiencing any issues with your slides or with your audio, start by refreshing your browser. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you're having any technical problems with the audio or with your slide presentation, again, try refreshing your browser, or you can click on Help in the top navigation toolbar for additional troubleshooting steps. But if you do end up needing a technician, just type a message in the Ask a Question box, and our tech team will get to you as quickly as possible. Any individual user experience questions, I'm having trouble seeing the slides, I can't hear the speakers, those will be answered in that Q&A widget below the slide presentation. Now we're going to have a word from our sponsor, Starline, so stay tuned, and we'll get the webcast going right after these messages.
For data centers worldwide, Starline track busway systems support the ever-increasing power demands of IT infrastructure. Our remote plug actuation system provides hands-free plug-in unit engagement, enhancing flexibility and safety for those working in critical spaces. Trusted for over 3 decades, Starline continues to pave the way for electrical power distribution systems for mission-critical environments.
Perfect. Now we get to the good part where I get to introduce our wonderful speakers today. We'll start with Chris Ossian, Product Manager at Starline. Chris is responsible for a global portfolio of data center products at Starline, including busway and metering products. He has over 15 years of experience in product and application engineering roles. Brian Burgess is a Technical Services Manager at Starline. Brian's responsible for the sales and operations of the field services at Starline and has developed and deployed service strategies that help clients achieve their current and future goals of maximum uptime. That's it for me here at the beginning. I am happy to hand things over to Chris.
Well, hey, everybody. Thanks for joining the webinar. Just a few more comments on myself and my background. Like Gary had just mentioned, been working in the space for about 10 to 15 years, mostly as an application engineer, and most recently as a product manager. Most of that time was spent in the data center space, specifying busway into data centers. And now I'm in charge of the global portfolio for Starline busway and in the data center space.
Hey, hello, everybody. A little bit more information on myself as well. So fairly new to the world of data centers, but I've spent the past 15 years working in high and medium voltage power distribution systems as a technician and as in operation. So pretty extensive background in power distribution, and all that translates well here, especially with the increase in power demands and densities in data centers. So thank you, Chris.
Okay. Thanks, Brian. So let's go over a quick agenda here. We just went through introductions. For those of you who might not be as familiar with the busway system, I am going to spend a few minutes just doing a busway overview and kind of give you a background of, of busway design and in data centers. And then we'll jump right into the impact of AI on power systems. Focusing a little bit more on Starline, but I'll also comment on upstream and downstream infrastructure. And then we'll jump right into the 5 key safety strategies. I'm gonna describe some of the strategies that we're seeing to help increase safety, especially in the data center space. And then I'm going to share that platform with Brian, who's also going to comment on a couple of the key safety strategies that we're seeing in the field as well. After that, we'll do a Q&A session. So feel free to put in any questions that you guys have during the presentation. We'll do our best as time allots to answer those questions once we're done with the content of the presentation. Okay, so first off, wanted to describe what predated busway. And so I would say over 10 years ago, the legacy system that we commonly saw in the data center was an RPP system. And that RPP system, you can see the image on the top, started with the PDU, then landed to an RPP, which broke out the power into several different electrical paths that ultimately fed to the racks. And I think the important thing to note on that particular topology is that from the RPP, you had to route cables under raised floor to where the rack ultimately resided. So that routing that cables under floor really could result in clutter. We did see some inefficient cooling with that method as well. And then I think the gaping thing was that there was a potential for wiring errors because you were distributing it from the RPP, routing the cables under floor, and then ultimately ending up in the back of the rack. And so ultimately RPPs really took up valuable data center space with that type of topology. And that's really when busway kind of became a standard in data centers. It took that RPP topology where you would route power under floor, removed that, and pulled it overhead above rack. You can see in the bottom image, RPPs are no longer in the picture. Really, the power that was housed in the RPP is now distributed directly over the rack via the busway system. And the key advantage that you got from doing that was you really get a localized and visual view of how the rack is powered. So you don't use raised floor in that topology. Your A and B come in and they're powered directly above the rack using a tap-off disconnect. And so that overhead placement of removing the RPP and replacing it with a busway system really resulted in more efficient cooling, fewer wiring errors, because again, visually everything was much more organized. And I'll talk more in detail about it later in the presentation, but it also helps reduce the arc flash risk that presented itself with the legacy system as well. So just one more slide on the busway overview. I think two things to note here. One is the design. It is an extruded aluminum housing that houses copper conductors inside, both your L1, L2, L3, your neutral, and your ground. But I think the key thing there is that it's a U-shaped conductor, and that allows the Starline busway system to be a compression fit, both at the joints and for the tap-off units. And it really allowed for this modular approach to powering racks in that the busway is open channel and it's a continuous access slot and allows tap-offs to be plugged in virtually anywhere along the busway system. Now, with respect to data centers, you're seeing in this image with T's and elbows. In general, we don't see that in the data center space. In the data center space, we're literally just straight runs, A, B, along the top of the server rows, generally 30 to 50 feet long, and powering the busway below. And the second thing to note on this is at the bottom of the screen, you'll see our different amperages for the busway system. For this particular presentation, we start at 100 amp, but we do have lower busway amperage systems. But we started at 100 because that's really where we started to see data centers design in the busway system, again, more than a decade ago. So we started in that 100 amp and 225 amp space that was sufficient for that time. Fast forward about 5 years from there and 5 years back from here, we ended up sending a lot of 250 and 400 amp busway out to large scale data centers, hyperscalers, high compute areas. And we spent a lot of time and designs in that 250 amp and that 400 amp amperage. Now that we're seeing the market of AI and the popularity of AI racks grow in the last year or two, we're getting a ton more requests for more power and spending more time and energy in that 800, 1000, 1200 amp space that you see on the right. And you can see from 5 years ago, that's more than a 2x increase from the demand we were seeing 5 years ago. And so it's important to know that because we're just seeing this increase in power, and we have to keep in mind the infrastructure needs to keep up with that increasing power demand as we move forward. And so this next graph really drives that home. What you're seeing in the graph is the US power demand in terawatt hours projected up to 2030. Today, we're sitting at about 224 terawatt hours. You can see in the next 5 years, we're increasing roughly 400 terawatt hours in the US power demand alone. And so we're just seeing these higher power data centers across the US and across the world, demanding more power, not only from the busway system, but the power chain in general. And we'll get more into that in a later slide. But some of the infrastructure changes that we're seeing is removal of floor PDUs to help transfer higher voltages to the rack. We're also seeing higher efficiency transformers with higher kVA ratings, again, to squeeze more power out of the power chain. And really with this power demand, we're seeing more and more data centers needing to have trained personnel to deal with that risk. So with this increasing power demands, inherently, you're going to have higher arc flash risk because you're increasing the power. And with that, I think companies, organizations, employers all need to keep in mind that you need to equip your employees to deal with the work under that type of increased risk. So another slide on impact of AI and power systems. This is kind of taking a more narrow look and going down to the racks, the containment, and the busway system itself. As I stated earlier, we are seeing this surge in amperage requirements, and I talked to that earlier with the busway systems, but we're also seeing it from the ground up. So on the bottom image, you're seeing kind of the evolution of rack power from, again, nearly a decade ago to now. We started in that 1 to 3 kilowatt space, and then fast forward to several years, increased to that 8 to 13 kilowatt space. Today, we're very commonly seeing 23, 24 kilowatts of rack power, but we're also seeing the roadmap of what some of our customers are doing as well, right? We're seeing requests that are coming in the next year for 50 kilowatts to 100 kilowatt racks. Beyond that, we're even asked 150 kilowatt racks. And in the long term, it's going to be even larger than that. So again, reiterating the fact that there's no stopping this increasing of power demand within the AI space. And just to comment on voltages here too, that second bullet shows three-phase voltages over time. Very commonly, 208 was a very prevalent voltage to be used at racks. Today, and even in the last 5 years, 415 became a very common and standard voltage for busway and for racks. And we're getting deployments of 480 now as well, where 480, again, you're squeezing a little bit more power by increasing the voltage and getting a little bit more bang for your buck in the power chain at that point. And then again, looking forward, 600 volt AC we're being asked about. We're customers and clients are inquiring about increasing voltages more to get more power out of it. There's obviously discussions and designs of moving this part of the power chain even to 800 volt DC. Suffice to say, again, not along with the amperage requirements increasing, the power demand increasing, we're seeing the infrastructure and the design being evolving to a point where we're trying to get as much power out of the existing infrastructure and evolving a current equipment to kind of keep up with these demands. And then the third bullet here is liquid cooling. As we're seeing the power demands increase, we're seeing the cooling methods also change. Liquid cooling has become much more of a popular way to cool in these containment units and as part of the power chain. Historically, we've seen hot cold aisle containment, various methods of air cooling within the data center. And that was, again, common for a long time. But with these AI racks increasing their power, the heat that's generated from these servers are so high that liquid cooling has become a lot more popular. We're seeing hybrid air cooling and liquid cooling as well within the data center space. And again, that ties into the evolution of infrastructure changing with the power demands increasing over time with these AI demands. So with that, I'll hand it over to Brian just to discuss a few challenges that we're also seeing in the space.
Yeah, so we're talking about just the power densities and how things have increased exponentially over the years. With my background, which is more industrial, where you're working in really high demand environments. So, the data center world is moving in that direction. So, and with that, becomes, we've got different challenges to address arc flash issues. I know, Chris, you're going to get into that on the, I believe on the next slide. So yeah, not a whole lot more to add right there. Wasn't ready for you to turn it over at that moment, sir.
Okay. So with that, thanks, Brian. We'll talk more about arc flash in a few slides.
There we go.
Yeah, as of now, we're going to jump right into key strategies. And so the main point of this is really to, the key strategies are to equip, the audience with knowledge. Feel free to take away what you see fit for your particular situation. And so key strategy one is really to use overhead busway architecture. I talked a little bit earlier about the legacy panel systems. And so for busway, really it helps eliminate exposed panels and reduces the arc flash exposure, especially during maintenance. And part of the reason it does that is because we have to comply to UL 857, which really allows a plug-in design to be robust in that UL 857 requires designs to be minimal risk, meaning we have to design it in a way where you cannot improperly install it into the busway, which again increases the safety for personnel when you're doing these live insertions. But UL 857 also has one other key point, and that's to establish a fault path before any of the live conductors actually make contact. The busway design is designed to do that. So whenever you're adding a circuit or removing a circuit, you're always going to have that fault path in place so that if something were to go wrong in the field as you're adding the circuit, there is a place for energy to go in the event of, say, a fault. So really, those two kind of key things from UL 857 really helped, energize insertion be very low risk with the busway design. And I'll also mention we have done voluntary testing with arc flash where we've intentionally set off a arc within the system and just kind of see how it behaved. And safe to say there was nothing catastrophic that happened with that test. It was an IEC test that we did. I forget the exact number offhand, but we did pass the criteria there, which gives our customers more confidence that the busway system itself is a very, very safe design. So we'll move on to key strategy 2. I'm going to spend a little bit more time on this key strategy because we're seeing the makeup of the Starline busway in general. We're seeing a lot of it change in this area with respect to the AI impact. And so if you're familiar with this, again, part of the power chain, for a long time, circuit breakers were really the standard to protect against faults and even in overload situations. For circuit breakers, it does the job it's supposed to do. It's supposed to open in either of those two scenarios, either in an overload or a short. And when that does happen, a user can go out and simply reset the breaker to allow for normal operation again. In recent years, we've seen this migration to fuses, and there's a couple of reasons why we're seeing that. One of the main reasons is that the clearing time for fuses we've observed to be relatively faster in circuit breakers. And if you have a fault and it clears that fault quickly, the incident energy or the arc flash energy that is generated from that event is cleared a lot quicker, and it's a less severe, which means your blast force from the arc flash is actually a lot lower as well. So fuses, again, clear quickly, which result in lower incident energies when you look at it from an arc flash perspective. But not only that, fuses, with this migration, again, to higher power infrastructure, we are seeing an increase in available fault currents at the busway system and upstream and downstream because of it. And so the withstand for fuses can increase all the way up to 100K, 200K as well. And so the withstand that we're seeing is more than sufficient to handle this migration to power with increasing power demands. And so really fuses have been somewhat of a preferred OCPD for AI, for high compute, due to the high speed protection demands that it exhibits. And then the two other things that are not noted here that are worth mentioning is this migration to liquid cooling that we're seeing have really put into consideration monitoring overcurrent protection devices within the busway system. We're seeing more requests to put in auxiliary contacts at the Starline busway or shunt trips or both, and the reason why we're seeing that change is because users, designers, they want to be able to know what's going on with the system, especially with the high compute racks. And they can do that using auxiliary contacts to get the state of the OCPD. But more importantly, if something does go wrong, say with the liquid cooling system, you have a way to trip that particular breaker or the breaker installed with the shunt trip and remotely open it to prevent further damage. So we are seeing more requests for this. And then the other overcurrent protection device change that we're seeing as well, or at least requests that we're seeing recently, is local disconnects at the end feeds. And we're seeing that because, again, in the event of some of these newer cooling methods, a user wants the ability to locally shut off power and not have to go to, say, an electrical room to shut off power in the event of something going wrong. So we are seeing changes in the field. Brian is going to comment a little on the arms breaker right now, which is something to consider too during maintenance. So feel free to discuss that point. Oh, I think you're on mute, Brian.
There we go. All right. Yeah, arms breakers that type of system is something that's widely used in the industrial environment. So in high and medium voltage systems, and basically it stands for arc reduction maintenance system. So basically it's a way for technicians to, whenever they need to perform routine maintenance on the system, to go out there and change the coordination, basically change the trip settings on the system. So, otherwise you'd never get the incident energy down to a safe level to where you could even approach the gear. So it's widely used, like I said, in more of an industrial environment when you're working with 15 kV, 5 kV switchgear. But we're starting to see it in the data center world now too, with the increase in power densities. So yeah, it's a great way. And in many cases, if you can't get that energy, that incident energy down to an acceptable level, well, then the system can't be worked on. So like you said, we're starting to see a little more of that in the data center world with the growing power demand.
Got it. Thanks, Brian. And with that, we'll go right into continuing on with the OCPD discussion. I think it's worth pointing out, again, this is still sticking with key strategy 2, to really look at selective coordination with your OCPDs, because you want to protect the equipment, but 2, you want to be able to contain a fault as well. And so what you're seeing here with the image on the right is a fault happening downstream, and that first overcurrent protection device actually opening up and limiting it to that part of the power chain. Whereas the image on the left, you see that same fault with an uncoordinated system. You can see that it trips virtually everything upstream, and it causes unnecessary outages. An unnecessary outage. And so the reason why we're bringing this up is that in these kind of high dense power infrastructures, really selective coordination will help you increase your uptime and obviously minimize your downtime. So selective coordination, I think, is something we need to pay attention to. And then going back to Brian's point, the coordination, like even for a maintenance mode, you have to balance it, right? To get into maintenance mode, you have to put it in that mode, but you also have to pay attention to what you're doing with the coordination itself and making sure that you do your maintenance and then you put it back out of maintenance mode to make sure that it's coordinated with the rest of the system. So there's a balance there that you have to strike when you're doing that maintenance mode. Okay, so for key strategy 3, arc flash studies. So this is generally required. And the reason why we have it here is we're thinking it's becoming more of a focal point for our customers now, and definitely moving forward with the increasing powers. And so what arc flash studies give you is really it evaluates your electrical system and gives you the metric for arc flash, which is incident energy. It gives you the incident energy levels at different important points in the electrical system. And when you have that knowledge, you can better protect your employees. So to further kind of dive into that, the image on the right shows your protection boundaries by this MDE. And in the center in red, you'll see that is your arc source. Outside of that, you have your restricted and your limited approach boundaries, which are voltage dictated. But the reason why we're showing this graphic here is that your arc flash boundary varies. You can see that by the green arrows that point left and right. Arc flash boundaries vary from site to site, and it's because it's dependent on the electrical system itself, right? Depends on how much available faults there, how much resistance and feed wires you have. So it really varies. And it's important to note here that with these increasing power demands, arc flash boundaries can be affected. And that's why it's important, if you weren't paying attention to arc flash hazard studies prior to this webinar, it's something you should be more of a focal point here moving forward, because it will give you the incident energy levels at each point in the system and busway. And with that knowledge, you can train your employees on what the arc flash boundaries are. And even for unqualified employees that maybe are less equipped to be in that zone, they need to stay out of that arc flash boundary. So to kind of finish this slide out, arc flash hazard studies obviously reveal incident energy levels, helps detect code violations, but it also supports compliance with NFPA 70 and OSHA requirements. OSHA requirements, I think, are self-explanatory. Everybody deals with OSHA, data center industry or not. But the NFPA 70E, it is not OSHA, but OSHA uses it as a guideline for employers to train and keep their employees safe. So getting your arc flash study done and paying attention to it really helps the organization, the company, the project as a whole. Basically equips them to be safe as they do any type of electrical work. And then key strategy 4, I'll talk about the first 2 bullets and then hand it over to Brian. You guys saw a commercial earlier for the remote plug-in actuator. It's the image on the left, and really this key strategy is about risk mitigation technologies, and the RPA fits really nicely into that. So for the Starline busway system, we have this capability to essentially, if you want to add a circuit in the field to a live busway, you can use this RPA to remotely engage the electrical conductors and make that tap box engage to the busway system in a live situation, but outside of the arc flash zone. So let me take a step back here. You can insert this tap off live into the bus without engaging any electrical conductors, install this remote plug-in actuator, step away from the arc flash zone and be outside of the arc flash zone up to 30 feet away, and then remotely engage the electrical conductors into the busway system while the busway is still live. So we really made this, and kind of circling back to an earlier slide, the busway is designed for energized insertion, still is, and up to even the 1200 amp it is designed for that. But we're hearing our customers concern over the rising power and some of the incident energies that we're seeing in the field. So we've created this device to help mitigate some of the risk that would put, kind of quell some of the safety concerns that a client might have with these rising powers. And then the second bullet here is really temperature monitoring, but the bigger picture here is environmental monitoring. And so really, if you install or implement some sort of environmental monitoring for our system, it's the temperature monitoring, you can really get ahead of any catastrophic failures before they happen, right? So for the Starline busway system, we can temperature monitor our terminations at the end feed, where we actually power the bus. And that provides real-time data to a BMS system. So in an instance where, say, there is a hot spot that's happening within the end feed, you can alarm the BMS system automatically to say, hey, there's a hot spot here, and then schedule some time to at least investigate it to see if it's a real issue or not. So it really helps prevent any catastrophic failures before they happen, well before they happen. So with that, there's another method called IR scanning that does very similar work, and I'll hand it over to Brian to take it over from here.
Yeah, I would imagine most everybody with us today is pretty familiar with what IR scanning is. Basically it's infrared thermography with a thermal camera. So, and I'll move to this next slide, and got a great picture here of something to look over. The cursor in the center of this image here, indicates the hottest temperature framed by the technician. So it's basically a handheld device with a screen on it where he can see this image. He can switch between this image of black and white, even with a color image. So he knows he can frame it first and then switch the scenes around to where he can see the different color variations. In the center there where the cursor's at, that's the hottest point. So you've got those 3 bus bars. The cursor can be programmed to either find the hottest spot in the image on its own. When it does that, it'll indicate that temperature at the top left there. If not, if you want to pinpoint it, the technician wants to say, hey, I want to see this particular spot, then you can set the cursor where it stays in the center, and then it points the camera and it'll give you the temperature. Over here on the right-hand side, this is basically a scale with all the color gradients. So, and it's going from 24.4 degrees Celsius is the coldest in the framed image there, all the way up to the hottest point. So it's a great tool. And while the technician's using it, say, hey, he notices an area that's of concern, you could take a picture with it. It saves it on the camera itself, stores it you could print it out later and put it in a report, add notes to it. It's just a great tool. What's the biggest thing about these is going out and doing an IR scan is it's a type, obviously, of preventative maintenance. So you've got a power distribution system that's up and running. You can go out there while it's energized and conduct these scans and discover potential issues. 90% of the time, it's a loose connection. These appear to be riveted on this bus bars right here, but it's typically a loose connection. Whether it's on an in-feed, if we're talking about a bus system, where the joints are made, or even the contacts on a tap-off box. So just a great tool. We're starting to get a lot of customers now that are working towards, they're actually ordering our in-feeds with IR windows already pre-installed. We have a lot of other customers that are, they have an older system that doesn't have IR windows, and we offer a retrofit kit to where, we can, depending on the type of in-feed you have, we can send those out to you, and then you can update your system that way. And now this is required under NFPA 70B. So NFPA 70B in 2023, January 1st, 2023, was updated from, it was a recommended practice to now it's a required annual, anything over 400 volts. So we're starting to, it's something that has to be done now, to where before it was just a recommendation. So something to keep in mind there, and that'll turn into a compliance issue, I'm sure. And then working over into PPE. So there's been some changes here. In the past, it was called HRC, which is hazard risk category. At that point, they actually had a category 0. They got rid of that. Category 0 was basically, what you'd wear in a data center, not performing any maintenance, but that's, hard hat, safety glasses, long sleeve shirt and pants, boots, just your typical PPE. Now it's recategorized. So we've got category 1 through 4, 1 being the minimum. And the thing to remember about all these different categories, these are determined by performing an arc flash risk assessment. Whatever category is prescribed, whatever you need to wear to work safely on that equipment is going to be defined by the arc flash risk assessment, which takes in a lot of things into account. So you're going to have a coordination study that's part of that. And then, NFPA 70E, it defines these approach boundaries according to the PPE category, but the category that you use, again, is determined by the arc flash risk assessment. This is something that has to be performed every 5 years. Once it's done, then labels are put on the individual pieces of equipment. And that way the technicians that are working on that equipment, they know exactly what PPE category they fall in order to do any type of maintenance. So you get down to the third bullet there, typical PPE requirements in data centers. It could be any one of those. There's no just blanket, hey, this is the typical. It could go from category 0, which isn't outlined here anymore, all the way to a category 4. 40 cal is the absolute maximum. So, the only place I could see that in data center use may be on the incoming switchgear. But other than that, you're going to see the other categories at play here. So it could be any of those. And again, it's all dependent upon performing an arc flash risk assessment. And then like Chris was talking about with the remote plug-in adapters that we have for our tap box units, I've seen those, those are great, right? So that it pulls you out of the arc flash risk boundary, because you've got a tether. So I've also seen them used on switchgear, to where we actually mount a external, like kind of an operator that controls the control handle on switchgear. So when you're doing any kind of operation, you can mount that to the gear, stand back from it, and you're out of that arc flash hazard area. Mimic panels, same way. It's basically a set of control handles that are mounted on the sidewall. It's out of the arc flash zone. And again, and it's all designed for technicians to safely operate the equipment and be out of the hazard area there. So now let me do the next slide here. All right, well, that gets us to our conclusion. So just to kind of wrap up, as Chris discussed, install overhead busway for safer, flexible, scalable power. Use overcurrent protection devices like fuses for faster clearing times. Went into detail on that. Perform arc flash studies to proactively detect anomalies. Should add a little bit on the end of this. Basically, if you're performing an arc flash study, the anomaly that you could detect and discover is in the coordination of the protection system. Utilize risk mitigation technologies to further reduce risk. And then at the very end of that is where proper PPE is the last line of defense. So all these other factors come into play. And then the bottom line is, obviously PPE is the last line of defense. We want to reduce arc flash risk as much as we can, get it to an acceptable level, and then wear the appropriate PPE. So I think that's it, Gary. If you want to get us into the Q&A, sir.
Sure, absolutely. I'm going to go ahead and just mention this. If you want to learn more or download Arc Flash Safety White Paper, there's a link there that should be clickable. I'll leave that up there for a few seconds if anybody wants to download that Starline Power link. And then, yeah, we will jump here into the Q&A session. So thank you, both of you, for all that great information. As a reminder, you can type your questions for our presenters in the Q&A widget below the webcast presentation. We'll get to as many questions as time allows. Anything that we don't get to today will be posted online at www.csemag.com. That is csemag.com, like consulting specifying engineer. Finally, remember to download a certificate of completion or a copy of the presentation. Use that additional resources tab on the right side of the screen. All right, I gave you guys like a 15-second break. You ready to jump into some of these questions?
Shoot.
All right, let's start. Let's see. Let's start with if a site hasn't, that actually seems like a really good place to start. If the site hasn't done an arc flash study yet, what is the first step? And then also, how often should this be done?
Yeah, I can take that one if you want, Chris. So it needs to be done every 5 years. The first steps are it's information gathering. So one line drawings, 3-line drawings, details of the protection scheme. And then you have to go out, you really need to go out and verify that information too. So a lot of times I've had clients in the past where they've got drawings, there's been modifications that weren't correctly noted. So sending somebody out there, a technician, to go out there and verify settings, verify the coordination, and then gather all that information, that's absolutely step number one. Mm-hmm. And then to answer on how often, every 5 years. But if there's been a change, so if there's been any kind of modification in the system, any kind of system upgrades, well, then you need to do another one at that point too, because that does change things dramatically.
Perfect. Can you expand on how IR scanning compares to live thermal readings in terms of safety and accuracy?
I can jump that one too. So as far as live IR scanning, so is whenever you have the your thermal readouts, right? It's an RTD. It's another device that could fail. So you've got live temperature readings on a piece of equipment. Say, hey, we're high on one phase here, right? Whether it's an in feed, we've got one of the phases that is hotter than the other. You still need to go out there and verify it with an IR camera if at all possible. Because again, an RTD, a remote thermal device, is just like any other device. It could potentially fail. So an IR scan is you're getting real-time information right there with the technician, with the camera in hand. But that's not always feasible, right? You're not always going to be able to, there may be equipment that, you can't get to it safely, or you can't open it while it's energized. So, they both have their pros and cons. The live temperature monitoring, that's going to be great in a lot of situations, but in most cases, you still want to go out and don't take that for gospel. You need to go out there and verify it with an IR scan and get a good solid image of it if possible.
What should commissioning engineers be thinking about when testing high-power AI loads?
Yeah, I can take that one too. These are all my questions.
Well,
um,
I'll mix them up
yeah,
here soon, but we're just
no,
starting
that
with
works.
you.
No, not mine, but they all apply to the services side of the business, which is great. Um, yeah, you need to. So, from a commissioning standpoint, you need to fully load the system. So, if you have an 800 amp bus and you're not sure, the original design is not to use that full capacity, you still want to load bank it to full capacity. So, with the way things are growing and progressing so quickly, um, if you only test it to a 400 amp load, and then down the line you add more IT racks, more load on the system, well, then you haven't proven it quite yet. So it's always, from a commissioning standpoint, it's always prudent to go ahead and load the system up fully to the full capacity, and run through your commissioning checks like that.
Mhm. How often do you recommend IR scans as part of a preventive maintenance program?
That's me too. It's an annual requirement.
Okay.
So, like I said, with NFPA 70B since 2023, they've moved it from a recommendation to an annual requirement on anything 4,000 volts and above. So it is an annual requirement now, and insurance is going to be a main driver in compliance on that.
Sure, sure. SCCR at rack is usually small, like 14 kAIC, while at busway it has more available fault current. How do you handle this situation?
Yeah, I'll take that one. There's a few questions in the Q&A regarding short circuit and rack power and it being a little bit lower. So we still generally see low rack short circuit, especially in lease spaces and colo environments. And the way that's addressed, again, is either fuses or current limiting breakers. We've seen a number of sites using the current limiting feature to essentially knock down the available fault to the rack to something it can manage, typically below 10. And again, fuses are very good at that. And there are circuit breakers with current limiting on them that will help in situations like that as well. So good question, because again, with the increasing power that we're seeing, I think that's going to come up frequently as we move forward as well.
Mm-hmm. For AI, oh, there we go. For AI loads, what's the highest tap-off breaker rating that Starline offers?
Yeah, so I'll take that one as well. So the tap-offs in general can go all the way up to around 500 amps, and those are large breakers. In a normal scenario with our smaller footprint of tap-offs that we offer, 100 amp, 125 amp is the max in the small footprint, but we can go above that with some custom enclosures if there is a requirement for above that amperage. And we are working very hard to optimize those custom designs, because again, we're seeing these requests here in the near future kind of exceed your standard rack powers that we're seeing today. So that is something on the radar, and we can work with you if you have a project where we can help kind of customize and hopefully make it as optimal as possible with such a high current.
Perfect. In a data center environment without circuit breakers, is it advisable to use reusable or resettable fuses instead of traditional fuses to maintain continuity and avoid frequent replacements?
So I'll take that one as well. We have not seen that in general. Again, I talked a lot about this migration to fuses, and we've seen most projects accept that they need to keep spares on site. So in other words, if you do plan to go to a fuse solution within the Starline busway system or anywhere, you should plan to have some sort of spare on site, because once that fuse does its job and opens up, you will need to replace it in the field.
Got it. Can IR thermography be used to evaluate phase load imbalances?
Yeah, I can jump on that one. Yeah, that's a great question. It can, right? So you're going to see whenever you have the thermal image up there, if one phase is warmer than the other, hotter than the other. So that is something that a technician that's trained on a FLIR camera or a thermography camera will be trained to recognize. So yeah, you want to, typically all three phases should be really close in temperature. If you've got a variation on any one of those phases there, then it's a good indication that you got some imbalanced loads there. So for sure, absolutely. You're going to use that information in conjunction with if you've got any electronic relaying or metering to see that as well. But yeah, as far as just things are getting hot, you've got a loose connection. Sure, it's a great tool to use for phase imbalance.
We've got about 9 minutes left here, so just as a reminder, if you've got questions for our presenters, put those in that Q&A widget below the webcast presentation. We'll see if we can get several more of these in here. Can I add plug-in units to the busway without wearing PPE?
Yeah, I think that's, Chris, correct me if I'm wrong here, but you can, right? And I think a lot of that's going to go to what the facility requirements are. And what they determine as proper PPE. But yeah, our busway is designed to where you can do that. There's a ground in there that's always going to give a path for any kind of fault current whenever you're plugging or removing the tap boxes. So you will be isolated from the fault current per design. Correct, Chris?
Yeah, let me add to that real quick. And this goes back to both Brian and I presented on it. It's the arc flash studies. So if you have any incident energy, say it's even 3 cal per centimeter squared, it's recommended that you do have some sort of PPE. If you're going to do it live, if you have something extremely low, maybe close to 0, you still have to follow whatever the site requires. And if I don't think there's a rule of thumb to say you can't use it entirely. I would lean on whatever your site rules are. But typically that means leaning on the arc flash study to tell you what you're actually dealing with. So I think at the low end, it's non-flammable clothes and safety glasses. But Brian had also a kind of a PPE recommendation based on incident energy as well. So again, all it comes back to is arc flash studies, what type of PPE and incident energy comes up from that. And then following that is whatever your site rules are as well.
Can you gentlemen provide some details, a little bit of information on Starline remote operation outside of the arc flash hazard zone?
Yeah, I'll jump in there. So there's a couple questions around the RPA. You guys saw a commercial about it earlier. So you would use it in a situation where you want to, in a live bus situation, where you want to do energized insertion, but you want your personnel that's actually doing the install further away from wherever you're plugging into. And to re-say that, what you would do is you would, generally in a data center, Starline busway is mounted above 10, 12 feet above racks. You would take a tap off and insert it into the busway, but not engage any electrical conductor. We have a mechanism there to lock it into place without even, again, engaging L1, L2, or L3. At that point, you would plug in a separate tool, which is the RPA, right into the plugin itself, and then climb down from the ladder. The RPA has both a wireless and a wired option. It offers up to 30 feet of distance from wherever the RPA is at. So you would climb down from the ladder, get out of the arc flash zone up to 30 feet away, and then remotely hit a button for you to either engage the tap off insertion, but it also has a mechanism to remove as well. So not only is it meant for adding circuits in the field, say if you're adding a new rack to a busway that's already in operation, if you want to disengage one, it can also do that. So it does the exact opposite mechanism where you can, again, attach this RPA to the tap off and step away from the arc flash zone and hit the remote to disengage the electrical conductors from the bus system. So we do have material out on the starlinepower.com webpage. And I think it's worth saying too, if it wasn't clear already, tap-offs do need to be designed for that, that RPA tool. So out of the factory, it needs to be equipped with what we call a rotating paddle. And that allows us to, again, have a remote operation, have a tool, disengage and engage the electrical conductors into the busway system.
Another question for you on RPA. I don't think it's overly repetitive, but so I think this will cover new ground, but let's try. If you could remote operate an RPA to engage and energize, can you reverse the operator and de-energize it and remove the RPA if needed?
Yeah, Gary. Yes, you can, for sure. Mm-hmm. So you can add a circuit to a live busway, or you can disengage it. And I think one extra piece of information there is this handles the rotating paddle to engage or disengage the electrical portion of the tap off. But you still, when you're doing this, have to have your breaker in the off position as well to make it even safer for your personnel to add these circuits or remove them in the field. So there's definitely several mechanisms you can use when adding or removing these things live. So where your risk of adding or removing a circuit is very minimal.
We've got a little less than 4 minutes left, so we'll try to get 2 or 3 more questions in if we can. What are the typical AIC ratings for the busways?
Yeah, I'll take that one. So we'll kind of start at the bottom. And so in data centers, generally speaking, we have the bottom of our T5 family, we call it, is 250 amps. And then the high end is 1200 amps. And so the short circuit is going to range from around 35K AIC, and I believe that's around 480 volts, all the way up to 75K with our highest version of it. So as you go higher in amperage for the busway system, the short circuit withstand of that particular busway system will also increase. And I'll say if you're designing a busway and you have a situation where your short circuit may be higher than what the busway can handle, we do have some test data, or we can do test data to look at overcurrent protection devices upstream from the busway to knock down and make sure that withstand, coupled with the OCPD, is at an acceptable level.
Got it. What is the means of support for the OH busway system?
So the support system we have essentially hanger mounting mechanisms, our own. And I'll talk to data center specifically. So we have several mechanisms, and it depends on which buses you use and how much it weighs. But we basically call it a hanger mount, which attaches to the top channel of the busway. And in a data center environment, we usually see that proprietary mounting mechanism attached directly to Unistrut. So that's a very common install, but we have also seen, we've also seen mechanisms where you would use a similar mounting mechanism, but attach it to, let's say, a threaded rod instead. So there's different mechanisms depending on the application and where it's going. We're saying we also have mounting mechanisms and busway systems to help with seismic situations too, if you're in an area where you need to address something like that.
Perfect. Unfortunately, I think we're going to have to leave it there. We don't have too much time left. Thank you so much, everybody out there, for all the great questions. Really, really terrific Q&A. Gentlemen, Chris, Brian, thanks for spending your time with us today. Some really great information in this webinar.
Good deal.
Appreciate it.
Thank you.
Thank you so much.
Absolutely. Now that we are just about done, we're not quite done yet, please take a moment to answer a few questions on our exit survey. That's going to pop up on your screen here in just a moment. We use these answers to help make improvements to our webcast program. On behalf of Starline, Legrand Company, and WTWH Media and Consulting Specifying Engineer, thanks so much for joining us today. We'll see you next time.